I want to do a little introduction to groundwater here by talking about the properties of materials, we call them porous media, that water passes through. So really important point, for most groundwater system, groundwater flow occurs through the tiny pores present in rocks or sediments. It does not move through large channels like you may have seen in a children's book where there's a river of water flowing underground. That sometimes happens, but it's incredibly rare. And for most of the time, water is not flowing rapidly through these large underground rivers, but is flowing through little tiny pores. Now that is not to say that all the pores are exactly the same size, because they're not, but in general they're small, and therefore in general the flow is quite slow. You can see especially in some kinds of soils where there's a lot of larger openings created by organic material, by roots for example, there may be quite a variety of hole sizes. But regardless of the variety of hole sizes, most holes, most pores are small, and therefore most groundwater flow occurs through these little tiny small pores and is consequently pretty slow. We distinguish between two zones of water in the subsurface. In the unsaturated zone, we have the presence of both water and air. The water here is shown as blue, little water molecules clinging to the orange clasps, and the air is white. And in the saturated zone, all of the pores are full of water. There is no air. Now, in general, we call the boundary between the saturated zone and the unsaturated zone the water table. Though in detail, there is usually a small zone above the water table where the zones are in fact saturated, but that's due to the rise of water into those pores by capillary action. One way to distinguish between the saturated zone below the water table and the zone of saturation above the water table in the capillary fringe is to look at the gauge pressure of the water. By definition, the gauge pressure of the water is positive in the saturated zone and within the capillary fringe, and indeed within the soil anywhere above the water table, the gauge pressure is less than zero. So the water table would be defined then as that surface at which the gauge pressure is equal to zero. There is no weight, there's no pressure due to a weight of overlying water. Beneath the water table, the gauge pressure progressively increases, typically, as we go down. The capillary rise that produces the capillary fringe is related to the size of the pores in the overlying material. And in general, we'll talk about this a little bit later, the size of the pores is related to the size of the clasps, with the observation that we see the largest capillary rise where we have the smallest pores. So in soils that consist of lots of clay-sized particles, we could see actually capillary rise on the order of several meters. In Florida, where typically the soils are sandy, the capillary rise is very small, on the order of a few centimeters, which is why in Florida we typically just ignore it. Okay, let me talk a little bit about porosity, and then I'll talk later about permeability and hydraulic conductivity. But starting with porosity. Porosity is defined as it describes the amount of pore space available to put water in some kind of porous medium. It is defined as the fraction of the total medium that consists of pores. It's defined as the volume of the pores divided by the total volume, which includes both solids and pores. It's usually expressed as a percentage, and it typically ranges from anywhere around 0%, there are some rocks that have essentially no pore space at all, up to maybe 50% or so for some kinds of sediments. We distinguish between two different kinds of porosity. Primary porosity is porosity that forms at the same time the rock does. And we'll think a little bit about that in a second about what that means. Secondary porosity means porosity that is formed subsequent to the formation of the rock. And it is related to either dissolution, where materials are dissolved from the rock, or fracturing, where the rock is broken up and introducing fractures that can be used to store water as well. Here is an example of secondary porosity in a limestone. This hole here, as well as these tiny little holes here, are all caused by the dissolution of certain minerals out of the limestone, leaving behind pore space. Let's turn now to the concepts of permeability and hydraulic conductivity. Both of these terms are used to describe the ease with which a fluid can move through the pores of a porous medium. The two terms have slightly different meanings. The hydraulic conductivity, we use the large symbol K, means it describes the ease with which water flows through a porous medium. The fluid is always water. The dimensions of hydraulic conductivity are length over time, and we typically use it in units of either meters per day or feet per day for the study of groundwater. The permeability, we use the symbol kappa. That's a Greek kappa over here. The symbol, there it is right here. This is a little bit different. The permeability is a property of the medium only. It's independent of the fluid. It describes the ease with which any fluid can navigate through the pore structure of the porous medium. It has dimensions of length squared, and commonly we use either centimeters squared or meters squared in the metric system. So the idea is that hydraulic conductivity is a term that describes the ease with which water specifically can move through a porous medium. We can relate these two terms together if we know the properties of the fluid. So in this equation here, we have the hydraulic conductivity K here, and we can see that this can be expressed as a function of the permeability and then the other terms in blue, which are functions of the fluid, the density of the fluid and the viscosity or the stickiness of the fluid. G is the gravitational acceleration due to gravity. Well, why would we want to use the idea of permeability instead of hydraulic conductivity since we're normally worried about the flow of water? Well, the answer is that sometimes we're not worried only about the flow of water. For example, petroleum engineers typically have to solve problems in which there are three different fluids moving through the subsurface. We could have gas, we could have oil, and we could have water. And not only that, but the water itself may be very, very different. We may have super briny, super high concentrations of dissolved solids. We may have nearly fresh water. And all of those fluids have very different physical properties. And so they would require us to invent different kinds of hydraulic conductivity terms that are related to each individual fluid, and that's just way too complicated. And so petroleum engineers, because they deal with fluids of such different properties, typically use the permeability to describe the ease with which any fluid can move through the solid, and then link that to the properties of the fluid when they want to understand how quickly or easily each of these different fluids moves through the medium. In contrast, groundwater hydrologists are typically talking about fresh water. For us, when we're talking about water flow relatively near the surface, the fluid is nearly always water, nearly fresh water, and so it makes a lot more sense for groundwater hydrologists or hydrologists in general to combine the properties of the fluid and the properties of the medium into a single term that describes the ease with which water flows through a porous medium. And that is what we're going to do in this class. We're going to be talking mostly in terms of hydraulic conductivity because we're most interested in water. So let me talk a little bit about the values of the hydraulic conductivity or permeability. I may just call it permeability or I may call it hydraulic conductivity, and I'm not going to ask you to learn the actual values, but I'd like you to understand the relative values of either hydraulic conductivity or permeability in various types of materials. So let's start out by considering the relative values of hydraulic conductivity or permeability in sediment. The big idea here is that in most sediment, there's plenty of porosity. And so the control on the ease with which water can move through sediment, the permeability, is mostly about the size of the pores. So in general, the smaller the pores, the more difficult it is for water to flow through those pores. So clay sediment would have a lower permeability or hydraulic conductivity than gravel sediment. Again, the basic idea here is that if we actually look at this and do experiments, all accumulations of sediment, regardless of their size, have about the same porosity. It's on the range of 40 to 50 or so percent. So whether it doesn't matter whether the pores are big or whether the pores are small, if we take a bunch of equally sized pores and we pack them together and we pile them together, we'll find that we have about 40% or so pore space. Now, it is true that if the sediment is poorly sorted, the finer grains can fill in the pores between the larger grains, and so very poorly sorted sediment can have a smaller porosity. But in general, even in poorly sorted sediment, there is no limitation on the amount of pore space. There's plenty of pore space available for water to flow through. The key observation is that the size of the pores is related to the size of the clasts. And I think you can see that really nicely on this figure, which arranges clasts from large on the left to very, very small on the right. And hopefully you can see that the size of the pores, although it's not exactly equal to the size of the clasts, the pores between the large clasts are larger than the pores between the small clasts. And the idea here is that the friction that water flowing through those pores feels is felt at the interface between the pore and the solid, which is on the outer surface area of the pore. So if we imagine a pore is a sphere, it's a simple assumption here, we can look at the ratio of the area, the surface area of that sphere, which is 4 pi r squared, to the volume of that sphere, which is 4/3 pi r cubed. And we find that the ratio of the area of the pores to the volume of the pores is inversely related to the size of the pores. In other words, when the pores are really small, when r is a very small number, this ratio is really large. In other words, if we have a certain volume of water in our rock or in our sediment, and the pore spaces in which it is contained are really, really small, that means that though that water is feeling an incredible amount of contact with a very, very large surface area. And therefore, since the friction occurs along those areas, the flow of that water through that medium with very, very small pores will be hindered by all that friction and therefore will be slow. So once again, the idea is that the smaller the pores, the more friction is felt by the water in those pores per volume of water contained in the pores, and therefore the large friction will slow the water down and make it more difficult for that water to pass through the small pores compared to large pores. Now, turning to rocks, we get a different situation. In rocks, the porosity is very often very, very small. And in rocks, in many cases, it is the porosity that is the limiting factor on permeability. So it's not the size of the pores as much as it is whether or not pores exist in a rock. Many rocks, like the rocks shown here, have extremely low porosity. And if you don't have pores, you can't move water through the rock at all. In other words, the permeability will have to be very, very low too if there's very, very low porosity. We can think about different kinds of rocks. Plutonic rocks, plutonic igneous rocks, and metamorphic rocks form at high pressure. And under these conditions, any pores are sort of squeezed shut. So typically the porosity of metamorphic rocks and plutonic igneous rocks is very, very small, much less than 1%. And for that reason, these rocks have extremely low permeability or hydraulic conductivity. Volcanic igneous rocks often have a fair amount of porosity. They may have vesicles, as shown on that basalt on the left, or very often the surface of a lava flow, a volcanic lava flow, is often broken up and fractured, producing lots of pore space. So volcanic rocks, in contrast to plutonic igneous rocks, often have sizable porosity and therefore have sizable permeability or hydraulic conductivity. For sedimentary rocks, it's all about the cementation. Remember, the way you make a sedimentary rock is you take clasts, either terrigenous clasts eroded off the land or biogenic clasts made within the basin of deposition by precipitation. Those clasts fall to the bottom, they get deposited, they get squeezed together, and ultimately they get cemented together by some kind of mineral cement. But cementation is not always complete. In other words, in some cases, the clasts are not entirely I should say the pores between the clasts are not entirely filled with cement. As in this picture here, there is some pore space that remains. This is an example of primary porosity. So sedimentary rocks, in contrast to plutonic, igneous, and metamorphic rocks, typically have a fair amount, or sometimes I should say, have a fair amount of primary porosity, which then gives them a relatively higher permeability compared to plutonic, igneous, or metamorphic rocks. So for rocks, the permeability is not controlled so much by the size of the pores, but by the amount of pore space available. So in general then, most igneous and metamorphic rocks, especially plutonic igneous rocks, have very, very low porosity and therefore very low permeability or hydraulic conductivity. Sedimentary rocks tend to be more variable because they have variable degrees of cementation, which means that their permeability or hydraulic conductivity is more variable as well, ranging from very low if they're very tightly cemented to moderate if there's a fair amount of primary porosity. Now the one on the bottom is the wild card, limestone. And the reason is that the porosity of limestone is very, very variable because it varies not only due to the amount of primary porosity, but many, many limestones have experienced secondary porosity by dissolution. So remember, the limestone's made up of calcite and aragonite, and those minerals are relatively easily dissolved by waters, and that commonly occurs, leaving behind voids. So limestones very commonly have enhanced secondary porosity due to dissolution, which increases the porosity and therefore increases their permeability. Here's a couple examples. On the left, there's a limestone with a relatively low porosity, and on the right, there's one with a very high porosity caused by secondary dissolution. Here's another crazy example of a limestone that looks like Swiss cheese because so much of the original rock has been dissolved away, leading to enormous degrees of secondary porosity and an extremely high hydraulic conductivity or permeability. Here is, in the contrast, an example of a limestone that's got virtually no porosity. It's got no primary nor secondary porosity. This rock acts like a granite, a plutonic igneous rock with extremely low porosity and extremely low permeability. I think this sequence of pictures is really good. These are photomicrographs, or images taken through a microscope of 3 different limestones. On the top is a limestone with incredibly low primary porosity, no secondary porosity. This rock has an extremely low hydraulic conductivity or permeability. The 2 rocks on the bottom, in the 2 pictures on the bottom, the porosity has been enhanced by coloring it blue. On the right, we have a rock called an oolitic limestone. This is actually a rock, but you can see that there's a tremendous amount of primary porosity in blue. It looks like it's almost 30% or so. This rock is going to have a very high hydraulic conductivity or permeability because it has a very, very high primary porosity. On the left is another limestone that had a low primary porosity, but all the areas in blue represent areas that have been dissolved away, and so the rock down there has a very high secondary porosity, and it too is going to have a high hydraulic conductivity for a different reason than the rock on the lower right. It's got a high secondary porosity, but it doesn't matter what the origin of the porosity is. If you have a porosity that high, that rock is going to have a high permeability or hydraulic conductivity. So here's a table that summarizes those results, and I've organized it by arranging the permeability from, in general, low to high. So it's generally going up in this direction. So igneous, plutonic especially, igneous and metamorphic rocks have extremely low porosity, extremely low permeability. Most sedimentary rocks have a relatively low porosity due to incomplete but mostly complete cementation and therefore have a relatively low permeability. And then we get into sediments where the permeability ranges from very low in clay sediments all the way to pretty darn high in gravelly sediments with large clasts and therefore large pores. And finally, we have the very bottom of our table here, the one that's the wild card, which is limestone, which can have a permeability ranging this entire range here. It can extend from all the way, let's see, where am I? It can extend all the way from the lowest of the low to the highest of the high. The highest permeability materials known on Earth are actually limestones, and they also are some of the lowest permeability materials known. So limestone in green here is the great big wild card because its permeability is critically dependent on the degree of secondary porosity, and secondary porosity generation is very, very common in limestones.